Good afternoon. We are going to start lesson 18, which is on a new subject. It is a new module on sequence control. So, we are going to have our first introduction today on sequence control, on the kinds of controllers that are used for sequence control, namely programmable logic controllers or PLCs, and we are going to take a first look at the programming languages, the languages which are used to specify control programs for PLCs. So, as usual, we will first look at the instructional objectives. So, after learning the lesson, the student should be able to state three differences between analog and sequence control. This is important because traditionally an electrical or manufacturing or chemical engineering student is typically exposed to analog control, while the kind of control that we are considering here are different in nature. So, it is important to understand the differences between analog control and sequence control. Obviously, we should know she should be able to give an example of industrial sequence control, an actual practical example, and he should the programmable logic controllers or controllers which are primarily used in the industry to implement sequence control. He should be able to know three of its major functions, the major functional characteristics. He should also know the major components, the major structural components of the PLC, and he should be able to describe a typical program execution cycle that takes place in PLCs and how these program execution cycles affect the control performance. And finally, he should be able to know what are the typical elements of a relay ladder logic program, which is one of the programming languages which is used for programming a PLC, and know the various interpretations of the symbols used in this language. So, first of all, let us try to understand what is sequence or logic control. So, as I said, it is fundamentally different, not fundamentally, maybe very significantly different from analog controls on various aspects. So, we need to understand what it is. So, I constructed an this is my definition, words are mine. So, it is a class of control problems for systems where inputs, outputs and feedbacks are discrete set valued. Actually, I would rather say that they are, for the purpose of control, it is taken that they are set valued, that is, the intermediate values are not considered. So, for example, a switch, it stays 99.999% of the time in on state or off state, but obviously it goes from the on state to the off state, and that timing is so short that we choose to ignore it. So, we say that a switch is a system which stays in either one of two states. So, it is either on or off. We actually choose to ignore the times when it is going from on to off, because it is too small and of no consequence for us. So, in that sense, the inputs and outputs and feedbacks are discrete set valued like on off, and the problem is to cause or prevent occurrences of either particular values of outputs or combinations of outputs. So, when the switch 1 is off, switch 2 should not be on. So, giving an example from daily life, if let us say let us take a daily life example of a railway crossing. So, if the incoming train coming sensor is on, then the gate should be off. So, some particular combinations are allowed and some particular combinations could be prohibited. So, the purpose of control is to ensure that in all future behavior of the system, those combinations of outputs either must occur or cannot occur as is specified. Similarly, we could also have timing restrictions. So, you can say that after the train coming sensor becomes on, within 1 minute the get closed sensor should become on. So, now you are giving some timing restriction. So, you must ensure that the system, that the gate becomes closed within 1 minute of the train coming sensor becoming on. We might also like some given sequences of outputs, right. So, for example, suppose let us take a buffer where some machine is producing parts and then putting them in the buffer, and the buffer from time to time gets emptied. So, the states through which the buffer goes, so maybe the buffer capacity is 2. So, and every time the machine is dropping a part, the buffer is getting filled. So, the buffer should never go to the overflowing states. So, it should go to part count 0, part count 1, part count 3, then empty part state, and then again come to part count 0. So, the buffer should only go through certain states and should not go to some other state. So, only some particular sequences of outputs or events should be allowed, or there could be some given orders between various outputs. So, after this occurs, that must occur. So, these are sequencing orders, sometimes also called interlocks. If this has already occurred, that cannot occur. So, this kind of, so basically what we are trying to say is that if the system states are assumed to be discrete, this kind of statements are made about the desired behavior of the system, and then the problem of control is to realize them by exercising the inputs to the process. So, this is typically a sequence or logic control problem. Why they are called sequence or logic control? Because it is a finite state thing. So, it is described more by logical methods than by numerical methods. Before we look at them in more conceptual ways, let us take an example. So, look at this. This is what is it? It is supposed to be a die. It's supposed to be a stamping press. So, if you look at this, then so this is the stamp. This is the press. Okay. So, there are two solenoids, up solenoid and down solenoid. So, if the up solenoid is energized, these are hydraulic presses. So, if the up solenoid press is energized, then the pressurized fluid flows through this path and goes into the machine. So, the machine is constructed in such a manner that then this press goes up. Similarly, if the down solenoid is energized, then this press goes down, and this, so this is your metal sheet. It comes down and stamps on it. So, it keeps stamping, retracting, and creating a particular shape of sheet metal. These things are typically used in making, let us say, car bodies, right. So, it is a hydraulic stamp press. Okay. So, and obviously after so what happens is that it goes up, the up solenoid may be de-energized. So, whether it has reached the topmost position or the downmost position, this needs to be sensed. So, there are two sensors. This is the upper limit switch and lower limit switch, and these are the two actuators. The down solenoid and the up solenoid are the actuators, and this thing is our system. So, this is a typical example of a sequence control problem, where we are interested in only, see, the system is, everything is analog if you look fine enough. So, obviously the piston cannot the system cannot instantaneously come down from the up to the down state. But what we mean is that for the control of this system, we are not interested, for the sequence control in this of this system, we are not interested to know the intermediate states. We want to only ensure that if this machine is supposed to stamp, if that command is given, then it should periodically come down and then go up, come down and go up. So, only that we are only interested in, that is our control problem is only to ensure that it periodically goes through the up down, up down, up down sequence, that is all. So, in this sense it is a sequence control problem, right. So, this is there are n number of such other problems. For example, if there are many other application examples. For example, a plant startup shutdown sequence. So, when a plant is started up, initially you have to bring up levels to start. Initially automatic control may not be immediately applied. So, first you have to maybe fill some chamber. So, then start the pump. So, first open the valve, then you start the pump, then once the level starts filling, then you see when it has reached some sufficient level, then you switch off the pump, then you switch off the valve. So, basically, and then you start the heater. So, let the temperature come up, then maybe the automatic control will start. So, initially for these startup shutdown sequences, nobody, I mean you may not be interested in doing an analog controls, but rather the system is actually operated based on discrete controls. Similar things happen for shutdown sequences. So, once things have to be shut down, there are certain such some discrete control actions have to be taken. So, for such things typically sequence or logic controllers are used. Let us say conveyors. Conveyors are very widely used material handling systems. So, in conveyors you do not bother about what is going to be the motor speed, maybe you do not bother about that. So, you only have to start the conveyor or stop the conveyor. Maybe when you detect a part on the conveyor, you will start it. If you then after the part goes out from the other end, then you stop it. So, conveyors are typical examples where a lot of very simple PLC controls take place, sequence control. Similarly, there could be automated assembly operations. So, for example, you have a pick and place robo. So, the robo it goes to certain states. So, maybe it is situated somewhere and it is going to the picking up item X from the left hand side of the workspace, then putting it on the machine, then operating the machine, then again picking it up, then putting it on the bin which is on the right side of the workspace. So, the overall sequence through which a robo goes, or maybe picks an electronic component, places it on the PCB. So, such operations are typically described and controlled by sequence controllers. Now, we must understand that this is actually a robo. When it is for its movement, it has very sophisticated controls. It has servo motors in its various joints. It has analog controls on all of them. But here we are thinking of designing the controls at a different level, where we are not interested in that speed control loop is actually in place and it is working, but at a lower level. So, only this sequencing tells us that what set point to give at what time. So, it is a kind of set point sequencing if you look at it from the analog control point of view. So, based on the sequence of the digital controller or the discrete event controller, corresponding analog set points are being downloaded on the analog controllers, and the analog controllers are actually taking place and controlling the motion of the robo and then taking them through the final states. So, as far as the sequence control problem is concerned, we are not interested in knowing or in describing or in solving how a robo arm is moving from one point x y to another point x 1 y 1. We are not interested in that. We are just saying we are just making a mechanism by which the proper sequence of commands can be specified to the analog controllers, and then the analog controller will be expected to take care of that motion, right. So, in this sense it is actually a supervisory control problem. So, sequence and logic problems are often applied at a supervisory level, to provide set points to the analog controllers which are working below it at an automatic control level, right. So, similarly sequence control in CNC machines, where depending on the geometry of the part to be cut, depending on the machine configuration, sometimes you have to move the bed this way, sometimes you have to move the bed that way, sometimes you have to extract the spindle up, you may have to change the tool, you may have to switch on some lubricant flow. So, various kinds of again supervisory control actions must be specified. In fact, in a PLC there are, I mean it's if you see a CNC machine controls, then you can very clearly see that there are two different control systems, usually on two different control processors. So, you generally have a high speed microprocessor or a DSP, sometimes generally microprocessors, which take care of the analog controls problem, which are much faster, actually control the various motors. And you have a PLC, generally I mean G Fanu or whatever, I mean some make of PLC, and which will basically control these various motions and maybe also monitor the machine. So, supervisory control of robots, as I have told. So, sequence, that is why PLCs are used hugely in I mean this kind of discrete event control problems are very common in actually in industrial processes, and I mean you will find I mean literally hundreds of them. Now, we must realize, since we are, I thought that since we are this is a new kind of control problem, and we are the same motor or the same robo about which we learnt from an analog control point of view, we are still using them, but now trying to construct completely different types of models for them and trying to solve different types of control problems. It is useful to understand that a model of a process is actually, I mean what kind of model you will construct for a process entirely depends on what is it, which aspect of the system behavior you actually want to capture. So, it is not always. So, for example, let us say imagine that if you are trying to model a computer, then there are various architectural models for a computer. For example, there may be a von Neumann architecture, there may be a reduced instruction set architecture, there are several well known architectures of computers, I mean models around which computers are constructed. Now, computers are typically very large digital circuits, I mean sequential digital circuits, which are sometimes thought of as state machines. So, state machines are again have there are various kinds of state machines. So, when you are seeing the computer at the state machine level, then you are using models like Milli machine, Moore machine, basically automata theoretic models. So, again these state machines are made of what? They are actually made of digital circuits. So, digital circuits, how do we describe digital circuits? We know that we describe combinational digital circuits using Carnot maps or sum of product Boolean formula, or if they are sequential circuits, then we describe them as state transition tables. So, now what are digital circuits made of? They are made of transistors. Now, transistors are actually, the moment you come to a transistor, you have come down to the analog level. So, there you start describing voltages, currents and their time behavior. So, you have various kinds of small signal network models, either low frequency models or high frequency models. We have learned several kinds of models. Again, transistors are made up of semiconductors. So, semiconductors have physical models, electrons, holes, energy bands. So, you see that, but you obviously will not describe a state machine as a set of transistors. So, everything, so there is a whole hierarchy of abstractions. So, as you go up and up, you consider more and more things, and you consider them in more and more abstracted ways, But sometimes it also happens that the same device is being looked at as something by one person and by another thing as another person. For example, say if you are the user of a digital circuit, then you will use a model like I mean there are a NAND gate or AND gate or flip flop. So, you use one kind of models, but imagine the semiconductor, imagine the gate designer, I mean the VLSI designer of the gate. So, why you look at a gate not as transistors, but as a digital circuit, because you know that the circuit is such that for most of the time, just like the switch example I gave, it will either stay in a 5 volt state or a 1 volt state. So, it is either 0 or 1. So, it suffices to describe when it will go to 0 and when it will go to 1. It is not important at all to describe the transitions of how exactly the voltage signal will rise from 0 to 1, that is not important at all. On the other hand, the person who look at the VLSI designer who wants to design the gate. So, the gate circuit is such that it will automatically go from 0 to 1 or 1 to 0, but the beauty of design or the whole credit of design goes into understanding that how fast you can make it rise, how much less power can be dissipated and things like that. So, on the other hand, the circuit designer is mostly concerned about the transition part from 0 to 1. So, he obviously cannot take a view of the same gate as that of an AND gate model. He has to take a view of the same device as a nonlinear transistor circuit, because his attention is focused only on the transition or on the analog behavior, right. So, it is important to understand that. So, therefore, this is what I am saying, that even for industrial processes there is obviously analog behavior, everything is analog. But if we know that the analog behavior can be taken care of by the analog controls which exist at a lower level, then the problem can be simplified. If we assume the existence of suitable analog controllers, then the problem can be simplified to that of only specifying certain discrete commands, and how those commands will be realized, that is taken care of by something else. So, we are not interested in modeling that. Therefore, we will simplify the models and use different models and then solve sequence control problems. That is the whole idea, right. So, it is very important to understand that. If you look at continuous variable models, there the signals are real valued. Actually you have an infinite number of possibilities of values, and time is sometimes continuous, sometimes discrete. So, when we have continuous time models, then we have time continuously varying, but for all practical implementations, especially using computers, we must discretize time, that is, we must consider values only at certain instants of time. Now, you must realize that we are discretizing the time axis, we are not discretizing the variable value. Variable value axis is still continuous, variable value can be anything. So, but the time axis is sometimes discretized. So, that is why it is called a continuous variable models, where variables can take any value. Contrary to this, in discrete event models, which we are going to use for sequence or logic control problems, typically the values of variables that we will consider will be considering finite. So, let us say a typical example is on off, some tank level, low, medium, high. So, we are not interested in knowing what exactly how many meters, we are only thinking that the tank is in the tank level could take one of 3 symbolic values. So, each of those symbols actually represent some kind of an analog level value range. So, if it is 0 to 2 meters, we just call it low, we indicate it by a symbol low. If it is 2 to 4 meters, we call it medium, and if it is 4 to 6 meters, we call it high. So, we may define a control problem where we are not interested in knowing the value, but we are only interested to see that the moment the water level falls from high to medium, start the pump. So, we are interested in specifying such things. So, so discrete values over finite domains, and therefore, we have what is known as the finite state space. So, the combinations of variables that can exist in a system are going to be finite. Similarly, time, we have two kinds of models, this we are not going to see too much, but we have two kinds of models called synchronous and asynchronous, where we assume that all variable changes also occur at along with some clocks, just like a master slave flip flop is a synchronous device. So, or sometimes we have asynchronous. So, at any time certain variables can change. So, it is like time discretization here. So, if the time is, if variables can change from one value to another value at any point of time, we call it asynchronous. If it only happens at certain periods of clock ticks, we call it synchronous. So, this is the, so once we quantize, once we create a discrete this kind of discrete finite state description of the system, then it is easy to construct the, then we can construct the behavior of the system. So, typically we have in such systems three kinds of variables. They are the input variables. Input variables are some things which are applied externally. Okay. Then there are output variables, and then there are state variables. So, output variables are something which we can send, which we can maybe sense or see, and there may be some other variables which we cannot see, but the system goes through them. Okay. So, typically we consider systems, and in most of industrial control problems we have only a finite number of system states. Now, these states, what is behavior? Behavior is the pattern by which states change from, the system continuously moves, evolves from one state to another. Now why should the state change? The state could change either by an external event. So, a room was in dark state. Now somebody comes and gives an input or changes an input variable, say a switch from on to off to on. So, as a consequence of this, the room state goes from dark to lighted, right. So, this is a state change caused by an external events. Sometimes systems also go by, because of their internal dynamics, without any other external input given, it might change its state, right. So, there may be some arrangement in the system by which, suppose after it is made on, let us look at a monoshot timer. There is a common electrical examples. So, there may be something that once you press it, some bulb glows up, and then its dynamics is such that again after some time by itself, without any input being applied, it will come down. So, state changes are sometimes caused by external events and sometimes caused because of their own internal dynamics, they might come down. Similarly, state changes also, at every state there are some outputs which are exerted by the system. So, as states change, as the system goes from one state to another, the outputs are also changed, and these outputs changes are perceived in the external world, and they are sometimes called events, right. So, you could have events or outputs caused by state changes. So, this is, so when we have to describe a system, we'll presently see an example. We have to basically, whenever we want to model a system for the purpose of logic or sequence control, we have to find out which are the variables, which are the input variables, which are the output variables, how those change, what input exertion causes what state change. So, basically if we can describe these, then we have got the system model.